All right, good afternoon. Thank you very, very much for staying for the last talk of this wonderful meeting. And I'd like to tell you something very simple, that basically that all the hundreds of talks you have heard about superconductivity in this meeting don't take this very simple thing into account, which is the following. All right, let's start with a superconductor. We know has zero resistance and it has a Meissner effect. So there is a transition when we cool where what happens, you have seen it, but it's useful to see it again. This amazing thing happens that the magnetic field is expelled. Now that's a story in itself that I'm not going to talk about today. I want to think about the reverse transition where you heat and the current goes away and the system becomes normal. So that's the subject of the talk today. It's a reversible transition. We just saw it go in the two directions, and that's very, very important. So we are going to focus on the superconductor to normal transition when we raise the temperature. In order to understand what the problem is, let us first think about the normal metal. So how do I get to this state in a normal metal? Very simple. If I apply a magnetic field very, very quickly to a normal metal, it's not going to penetrate because of Faraday's law. Faraday's law is going to induce a counter EMF that if I apply the field within 10 to the minus 14 seconds, it just stays within a skin depth, which is basically the surface. And so I am in this initial state, and this is a normal metal. And now I let it evolve. And let's say this H is going to be HC1, but here in the normal metal, that's any arbitrary field. After some time, of course, the current will stop. And the way this happens is as the field penetrates, again, there is this counter EMF. And what I want to calculate is the work that the source, the electromagnet, is doing in getting the system to go from from this initial state to this final state. And that work is given by, I calculate this counter EMF, I calculate the work by doing the time integral of the epsilon times the I, and this is the answer, very, very simple. Now, the energy of the magnetic field that now exists in the interior of the sample is 1/2 of the total energy delivered by the source that is in this electromagnet creating this current. The other half is Joule heat. So all of this is exact calculations. Half of the energy delivered by the battery is dissipated as the current stops. Okay? So now let's do the same exercise, and this is proportional to the volume, so it's a lot of heat. Let's do the same for a superconductor. The same initial state, exactly the same considerations on the work done by the battery creating this current will give you exactly the same thing. And this is again the energy of the magnetic field, except that we cannot have Joule heat here because of what I said, that this has to be a reversible transformation. So how do all the supercurrents that exist initially and get induced in the process, how do they stop without generating Joule heat? That is the question. And also we can think about the initial state has both kinetic energy and angular momentum of the current. Where are those in the final state? Where do they go and how? And these are macroscopic quantities. For example, this is one example of what is this angular momentum of the current initially that is not there in the final state. So I just described to you two scenarios, one with a normal metal where I apply the field very, very fast to get to the same initial state as a superconductor. And I told you that there we have this Joule heat, and there we understand everything. We understand the energy conservation, and the momentum is transferred to the body as a whole, and the body picks it up by scattering and starts to rotate. But in this case, we cannot have any dissipation. So how does a supercurrent stop, and how is the momentum transferred to the body? That's what we need to explain, and everybody that claims to understand superconductivity needs to explain. And this is a very old question. So in particular, Kisom, who was a great experimentalist, spent 4 years doing lots and lots of experiments trying to understand what's going on here, because he realized that there can be dissipation. So in particular, he said it is essential that the persistent currents have been annihilated before the material gets resistance, because if there is Joule heat developed, we wouldn't have a Meissner effect, okay? Now, he said the persistent currents are annihilated by induction, and that's actually wrong, as I will show you. So he did not find out how it works. So let's think about it in more detail. As the system is here in the superconducting state, and here a magnetic field is penetrating. So near the surface, there is a supercurrent. Its electrons are moving very, very fast. And now the boundary is moving in. So what is happening? The boundary is going to move from here to here. So first of all, these electrons that here are not moving because they are beyond the London penetration depth are going to start moving when the boundary moves here. How this happens is very easy to understand. There is a Faraday field that's trying to oppose this transition, and that Faraday field is going to push these interior electrons to move and become now the surface current. And this Faraday field is also going to push the body to move in clockwise direction, in this direction, the positive ions. Now, the question we need to answer is, how do the electrons that are in the supercurrent here, once the phase boundary move here, how do these electrons stop? And in fact, the rotation of the body has to be in that direction, which is the direction of the original supercurrent, which is opposite to what the Faraday field is pushing the ions to do. And the total angular momentum that has to be transferred to the body is in fact much bigger than this initial angular momentum, because the Faraday field is pushing all the way as the phase boundary moves in the opposite direction than what the body is rotating. So all these are very simple and fundamental questions. And this transfer of momentum has to happen without dissipation. So the stopping of the supercurrent cannot be through scattering, okay? That's a problem. I wrote some papers on this, which you can go and look at to get details. So let me try to explain it in pictures simply. Here's the electron that is, I want it to stop moving very fast without dissipation. Well, there's only one way to do that. If there is a radial inflow of charge, if this electron moves in, and without going into details, the Lorentz force, which we all know about, is a charge times V cross H, points in that direction. So if the electron moves in, it will be stopped by the Lorentz force. No dissipation. At the same time, we need to have a compensating outflow of charge. So if this electron moves out, the same Lorentz force is going to push in this direction. And if we can manage to transfer that electron to the ions, then we're going to get momentum balance. So this electron stops this momentum, and the momentum got transferred to the ions. All right? And so we need to explain how does this outflowing electron transfer its azimuthal momentum without dissipation. All right, so let me do it in detail here. So this is the same picture, but so this is the outgoing electron. So let me tell you how it happens. There is a Lorentz force pointing this way, and there is also the Faraday field all along that points in the same way. And there is another force. And this other force is what I call F lat. This is the force that the lattice is exerting on this electron. And by Newton's third law, the electron is exerting a force on the lattice, on the body as a whole, that's making the body rotate in the right direction. Now, I know this is going a little bit fast and you probably are not understanding. Let me tell you that the same picture with electrons you can do with holes. And if you look at the forces for the holes, they are exactly balanced. The Faraday force goes to the right, the Lorentz force goes to the left, and yet this is transferring momentum to the body as a whole. To understand this, you simply have to realize that these electrons have negative effective mass, and that's the key. So you can understand all this in the context of the Hall effect. Materials with positive Hall coefficient, when you analyze what's going on, you have exactly the physics I'm talking about. When you look at what are the forces on the electrons, the force that the electrons exert on the lattice is what gives you the Ampere force in such a simple experiment. So the electrons transfer momentum to the body without dissipation when the Hall coefficient is positive, and that means when the effective mass is negative. And that happens for carriers, as you know from semi-classical transfer theory, carriers near the top of the band. So that is a basic message, that in order to be able to transfer momentum from electrons to the lattice in a reversible way, you need negative effective mass. As simple as that. You look at the periodic table, you see that superconductors have positive Hall coefficient, non-superconductors for the most part have negative Hall coefficient, which correlates with this very simple basic idea. You need negative effective mass or Hall carriers. So here's a summary. As I said, for the normal metal, you get dissipation. If you don't have Hall carriers in the superconductors, you cannot stop the supercurrent without developing Joule heat. Here I discuss the thermodynamics in a recent paper that came about because a very intelligent Russian physicist, Nikolov, raised this question also and said, there's no way this can happen without violating the second law of thermodynamics. Well, I'm saying that you can do it without violating the second law with electrons with negative effective mass. So all superconductors, this implies, have to have carriers near the top of a band. You can have multiple carriers, bands, but if you don't have carriers with negative effective mass, you cannot satisfy the laws of physics. Thank you very much for your attention, and I hope you'll have some questions.
I absolutely agree that there are flaws in standard interpretation of mass. No question.
Okay.
But the origin of this flaw is...
The origin of what?
The origin of this...
flow. You need radial flow. You need radial flow of charge.
No. Origin of the inconsistency of the theory.
Yeah.
Is based on... because all the theories of Meissner are based on London theory, right?
I'm sorry. Yeah, exactly. London
theory is based on postulate. Which postulate? Mu is 1.
Okay.
That what is needed, mu, the permeability.
Okay.
This is needed, necessary for London's statement that the field is expelled.
Okay, I'm sorry. We cannot go into details, but London theory does not explain the expulsion of magnetic field. When you integrate with time, you need to put, yes.
You can make the Meissner effect is B is 0, right? B is 0.
Yes.
What happens to A?
Okay, we can discuss this later. Are there other questions? Yes.
Why is it that we can't use, the premise here is that we can't use Joule heat, but you're doing a warm-up transition?
Yeah.
So I could imagine the resistance might be finite, could still have Joule heating?
No, that's the point. The supercurrent has to stop before the onset of resistance. Because if you have onset of resistance, you will have Joule heating. And Keeson realized that, in 1934, right after the discovery of the Meissner effect, he worked very hard to show experimentally there is no Joule heat. He showed to within 1%, he measured the latent heat, this Gorter cycle, the thermodynamics, he showed experimentally there is no Joule heat. He never could explain it. But if there is Joule heat, you can't explain anything. Even BCS theory is based on the premise that the transition is reversible, but BCS theory doesn't address the question, how is the momentum conserved and how is it transferred between the electrons and the body? BCS never deals with momentum, it only deals with energy. When you go into the Meissner state, the energy is lowered, but again, you have to explain how momentum of the supercurrent is compensated by momentum of the body as a whole. Those are unanswered questions. They haven't even been posed. They have to be answered. And so the theory that you have to explain the equilibrium state has to have the necessary elements to explain also these processes. And one of the things I've been saying is that if you have like a regular model of superconductivity with an attractive interaction or whatever, you cannot explain this momentum transfer. So that model, let's say a simplest attractive Haber model, if it is put in a magnetic field in a normal state and you cool it, it will stay in a metastable state. It doesn't have the physics necessary to expel magnetic fields nor to stop the supercurrent without dissipation. And we have to satisfy those laws. Yes?
So comparing it to the experimental situation,
Yeah.
let's say you just have a magnetic fridge.
Yeah.
And these have the superconducting fridge coils. When we're running these fridges, we worry about the fridge quenching because...
Well, if you all of this is when the transition is very slow. When it is very fast, you have all kinds of dissipation. When it's fast, you have Joule heating in the normal part because, of course, there is a Faraday field acting on the normal part of the sample. I am assuming that the transition is very slow, and so there is no dissipation due to just eddy currents and things like that. So any quenching will cause dissipation, no question about that. Yes?
So it's very clear, Tom.
Okay.
But I'm missing something. So
Yeah.
in the end, you basically made a statement, you cannot stop without unless you have next.
Yes.
And the last is it true that you're saying this and saying, since we haven't seen something that never start, it always start, then it must be a negative. Is that?
Yeah. Yeah.
So you're not excluding the possibility that maybe sometime in the future, someone will find something that doesn't start, then in that case, you will agree that maybe electron carrier would also be reasonable.
Well, but then there will be a room temperature superconductor because the supercurrent will not stop. Yeah, that's a great way to do a room temperature superconductor. Get electrons with positive effective mass to move. Yeah, then they cannot get rid of their momentum and satisfy the laws of physics, but that's not going to happen. Thank you. Yeah. So, right. So this, in some sense, is very, very simple. It's going back to Kittel, whatever, chapter 7 on, momentum and, momentum in semi-classical theory, curvature of the bands. I'm saying, and, when you look at, let me just skip to this, this is just a summary. That's another summary, but okay. So, for example, electron-doped materials, people said, okay, these are cuprates have electron carriers. So we predicted way back then that people will find holes. And in fact, very careful transport experiments over many years have shown that the electron-doped cuprates have hole carriers. And in fact, the holes are the ones that drive superconductivity. In magnesium diboride, as you know, there is also a band that is nearly full, that is conduction in the planes, that has hole carriers, and in the cuprates, the hole coefficient changes sign when you overdope, and in the transition metal series, you have exactly the same graph as in the cuprates, and again, you can see that the Fermi level crosses the top of the band right at the point where there is a kink in the hole coefficient. So there's a correlation, as I say, between effective mass in a wide variety of materials, okay? And for many years, we have been working on this. This is the A15, the old high-temperature superconductors. They also have hole pockets. And, what has not, of course, there are complicated materials that will have electrons and holes. But this concept, which I try to explain here, says there's just no way to satisfy the law of physics unless you have carriers with negative effective mass. Yes?
Correct logic. So you're not saying there is no possibility for electron carrier, but you're saying that you must have some hole carrier.
Yeah. That's what I'm saying. Yeah. Yes?
Vortices. Does a vortex motion produce Joule heating?
Okay, this talk only dealt with type 1 superconductors. Now, when you have a type 2 superconductor, and when you have vortices that are moving, yes, you will have Joule heating. But that is it's a different situation where you can also analyze these questions. But I'm restricting myself here to type 1 superconductors, to this transition that there is no vortices, there is just a first order reversible phase transition between normal and superconducting states. Yes?
You just showed that 10 and you just showed EV2. You those are type 2 superconductors.
I said that all materials, whether they're type 1 or type 2 superconductors, need to have negative effective mass. I'm sorry if my answer was not clear. Okay, this is part of a kind of larger body of theory that I and collaborators, in particular Frank Marsiglio, we have developed over many years. You need carriers near the top of the band in any type of superconductor, whether type 1 or type 2, in order to explain everything, pairing and transfer of momentum or so on. But I just meant to say that, you could have also dissipation in type 2 materials if, for example, there's current flowing, but that doesn't negate anything of this. You need negative M star for any superconductor, whether type 1 or type 2. Can anybody tell me why this is wrong?
Oh, yes.
Yeah.
But we will talk later.
Yes.
We can get pairing. I mean, you're looking at it as like it's a one electron puzzle.
Okay, I did not talk about pairing. That's an entire part of the story, which I'm happy to discuss. When you have the Fermi level close to the top of the band, there is a electron-electron interaction that becomes attractive.
Pairs have zero momentum, which we
No, the pairs have zero momentum when there is zero current. When you have a supercurrent, the pairs have Ck plus Q, C minus K plus Q. There is a center of mass momentum to the pairs. So you can think of whatever, this motion, but it's superposed to that, there is a supercurrent momentum. That's what we are talking about. I agree with you. I simplify the story. Yes.
So let's say I'm going to take a model where I just take some electrons p squared over 2m, turn on attractive interaction.
Yeah.
So
Yeah.
since there is no poles, are you saying to me that I will not have superconductor in there?
The model will give you a solution, possibly, where the energy is lower in the paired superconducting state, but that system, in reality, when you cool it in a magnetic field, will never be able to go to its ground state, because it doesn't have the physical mechanism necessary to expel the magnetic field. So it will stay, and all superconductors that we know of expel magnetic fields to a more or lesser extent, but they have the physics necessary to do this. And the physics necessary to do that, which I didn't really emphasize, is it has to break electron-hole symmetry. All this radial motion that I'm talking about is essentially tied to the fact that electrons are negative charge and ions are positive charge. And this whole thing of talking about holes as if they are electrons, that's all wrong. Electron-hole asymmetry is key. And these models, like the model you just described, it would describe the ground state or the excitations, whatever, but not the process by which the supercurrent starts or stops. It would not be able to do that. And I can take any bets on that, but if you want to work on that, I would be happy to discuss with you.
You know, I still would like to make a note.
Okay.
Field expulsion
Yeah.
is absolutely impossible, statement or whatever. This is, it can be possible only if, as it is assumed, postulated in London theory, superconductivity equivalent to vacuum. Properties of superconductivity, electromagnetic, is the same as properties of vacuum. That is, the base postulate of all London and then adopted in BCS and in Ginsburg-Landau, B equals to H, which is possible to only in vacuum.
Well, I think it's a matter of definition, what you call being okay.
H you can never compensate. All atoms.
Okay, you have an explanation of the Meissner effect that's different from you do. What is the physics?
Physics, this is just the same as diamagnetism, but diamagnetism in Cooper pairs due to learn more precisely.
You need to explain the process by which we start with no current, and when you lower the temperature, the current acquires momentum.
No.
Yes.
Oh, current is just circulate within the Cooper pairs. There is no transport current. No.
There is a current that creates a magnetic field in the opposite direction to the applied field, and I did not talk about that here. The physics that I say explains that is the same physics we just talked about for the superconductor to normal transition, which is you need radial outflow in that case of charge that will generate the Meissner current. And
There is
yeah,
no current.
okay.
Total current. There is no current. Impossible. Otherwise, it will break. It will never possible to.
Look, there is a famous Russian physicist that measured the change in the cylinder momentum when the supercurrent starts and stops. And that proves that there is a current that carries momentum. And when the current stops, the momentum is transferred to the body. And when the current starts, the body also reacts. And all that is proven experimentally. And that's Kikoin and Gubar in 1950. It's called the gyromagnetic experiment.
Kikoin was my boss, and I explained this experiment of Kikoin in this book very deeply.
You explain the experiment of Kikoin without any current?
Sure.
No way. The cylinder moves, it carries angular momentum. It was a sphere. The sphere rotates, right? So that means it has angular momentum.
No, yes. Whereas it is the same as diamagnet. Read the paper. I can give you.
It doesn't matter. Momentum is momentum. And there is no momentum in the electromagnetic field, so it has to be compensated exactly between the electrons and the body. There is no way out. This is elementary physics 001.
Read the paper of Kikoin.
I will. I have. I had a colleague, a Russian colleague, translate it to me, so I read it. Don't worry.
Good.
26?
46.
I'm not exactly sure. I read several papers of Kikoin. I'm not sure which one. Okay.
38. Just.
I read both of them probably. Most probably, yes.
How many authors?
Kikoin and Gubar is one.
It was the first paper.
Okay.
1946 in one and very thick paper. I can give you reference.
Okay.
You can find it in my reference.
I will look for it.
Yes.
What's your last name?
Jorge.
Okay, great. Any other questions?
Did you see this?
No. Okay. Well, thank you very much for staying so late. And no more questions, right? Yeah, sorry, go ahead. Yes. Yeah. Okay. I showed you an example of the electron-doped cuprates where people for many years said these are electron carrier superconductors. The particular case that you're talking about, I probably didn't see in detail, and apparently it may look like there are no holes. And if you can convince me that there are no holes, then I will say this is all wrong, because this is either right or wrong. And if you can prove experimentally without any doubt that there is no hole carriers in a superconductor, I would have to say that this doesn't apply to any material. But then I really look forward to somebody explaining how these processes happen in a different way. So I think in the particular example you're thinking about, maybe some complicated multi-band model, that situation that, right. Yeah. How do you know that for sure, that they have no hole pockets? Yeah, sometimes when there is a lot of renormalization, the quasi-particle weight can be very small and maybe you don't see it in ARPES, but it's there. And Yeah, I understand. But as I say, this applies to every superconductor. Either it's right or it's wrong. And if you can find a counterexample that proves it doesn't apply to that, I would have to say this is wrong. Absolutely. Yeah. Look, real systems are complicated, but physics is simple, okay? I mean, physics, when you listen to the talks in this meeting, everything, there's like a million different mechanisms and couplings and this and that. Look, maybe nature is complicated, but maybe it's not. I mean, Maxwell's equations are simple, right? And they apply to situations that look very, very different, but they are all same equations. This is a universal thing I'm saying that's very simple. Now, in realizations, you have complications, multiple band, but essential physics, I'm saying, has to be either right or wrong, and there is no ambiguity there. So I hope you guys will. So we have kind of, I think, not a full theory at all. So, the elements of a theory of superconductivity that, are really universal, and one, I think, has to, as I say, either prove it wrong or prove it right, but there's a lot of work to be done, okay? Because obviously, it's not a complete theory, and once we understand how superconductors really work, we are going to have room temperature superconductors, because right now people are looking at all the wrong places, in my opinion, and according to this picture, people are not looking at materials with Hall carriers. People are not trying to find materials where you have negative effective mass carriers experimentally. And that's what you should do to find room temperature superconductors. We can talk about what else you want so that EC is higher. It has nothing to do with light ions. It has nothing to do with light ions. It has to do with what you have in the cuprates and what you have in magnesium diboride. What's common to the cuprates and magnesium diboride? What is common is a lot of negative charge. In magnesium diboride, you have the boron minus planes, a lot of negative charge, and Hall carriers. In the cuprates, you have the oxygen minus ions, and a lot of negative charge in the plane, because there is one copper plus plus, two oxygen minus minus, and Hall carriers. Those are the conditions you want. In the pnictides also, you have negative ions. People have been focusing on the wrong ions. It's the negative ions, the holes in the negative ions that do it. And in things like the hydrides, even though there are experiments that suggest that they are superconducting, well, we'll see. The experiments are ambiguous at this point, but maybe I will be very happy if the hydrides are superconductors, then all of this is wrong. I'm saying that this is right. The hydrides, unless you figure out a way they can have negative effective mass carriers, they cannot be high temperature superconductors. So, yes. Well, it's not just most negative effective mass. You need to have the Fermi level close to the top of the band, but what determines the high TC, for example, is not just the curvature of the band, it's also the amount of negative charge. So the cuprates are satisfying those criteria. So you want to have very negative ions for reasons I didn't talk about in this talk, but and you need the negative effective mass. So yeah. All right. Okay. Thank you very much.